I also have to say that we are not very experienced using systems engineering, but doing this very large ReWater project, we realized that we had to do something in a more structured way than we normally do our projects. So that's actually why we have started working with Henrik and Sising AS. This is the agenda for my speech. First, briefly about Aarhus Vand, and then also briefly about the ReWater project, and then something about the background for us deciding to use systems engineering and the standard 81346. We have made a reference model of our plant. I will show you, and then we have made some analysis using the N2 approach, dividing everything into systems. Then we have made this analysis trying to discover all the interfaces between all these systems. And I'll just show you what we did there, what we found out. And then I'll wrap up. What are we going to do in the short time, and what are we going to do in a longer aspect of the project? So that's the agenda for today from my side. First, briefly about Aarhus Vand. We are a limited company, but we are 100% owned by the municipality here in Aarhus. We are 230 employees, and we serve 350,000 people here in Aarhus at the moment. And that's also the capacity of our existing wastewater treatment plants. And that's something to think about when we are now building this new plant for up to 600,000. We also deliver drinking water, potable water to the municipality, about 15 million cubic meters every year. Then we collect the sewage, and that's about 35 million cubic meters per year. And then you can say, how is that the difference? That's the rain and the water that shouldn't be in the system from the groundwater level rising and all that stuff. So we have a lot of water we are treating on our wastewater treatment plants. And then, of course, we have some pipelines, 1,500 kilometers of drinking water pipelines and 2,800 kilometers of sewage pipe. We have a business strategy. We have a purpose actually in Aarhus Vand, and our purpose is actually to create health through water for people and for the planet. And it might sound very on a high level, but we try to make a line of sight from all of our daily activities to this purpose. And then we have this strategy house, and in the foundation we have our excellent basic delivery services to our customers. We have to do that in an effective way, and we have to do it in a sustainable way, and we have to do it in a secure way. So that's actually in the foundation of all we are doing. And then we have a purpose-driven organization about the line of sight to our purpose. And we have 3 strategic focus areas that we are working with. And that's globalization, innovation, and commercialization. And that's actually our strategy. And then I'll present the Aarhus ReWater project. Many years ago, actually, we made a plan to centralize all our wastewater treatment. When I started 20 years ago, I think we had more than 20 wastewater treatment plants, very small ones and large ones. And in the first phase of this centralization, we decommissioned all the small plants, and today we have 4 plants of more than 100,000 people each. The largest one is about 200,000 people, and the total capacity is about 350,000 person equivalents. And Aarhus is a city that is growing very rapidly, about 5,000 people every year. And you can draw a line, and you can see when will the capacity be used, and about 2030, then we're doomed. So we have to do something. So the strategy is to then have only 2 plants left, one in the northern part of the city in EO, and a new resource recovery plant, as we call it, at Aarhus ReWater, with a capacity of 400,000 people in 2030 and about 600,000 people in 2050 or 60, or what the prognosis will turn out to be. The main components of this ReWater project, it's of course the ReWater plant itself, but it's also what you can see here is actually the small thin blue line is pipelines from the existing wastewater treatment plants to the new one, and the yellow fat pipeline is the outlet pipeline to the bay. We're going to have an outlet about 3 kilometers out in the bay. The green line is actually treated wastewater returned to 2 small creeks in the southern part of the municipality. So we are actually delivering some treated water to keep these creeks alive during the summertime, where there's almost no water in there. The location is actually at this moment not finally decided. We have 2 possible locations, both you can say at the end of the existing Marselisborg wastewater treatment plant, which is situated by the blue arrow. So we have what we call the main site, and we have another site, some kind of an appendix to the harbor. And it's up to the municipality and the politicians to decide which location is going to be the one. This is the preliminary master plan layout for the 2 different locations. The one on the left is somehow a kind of a wastewater treatment plant with a park on top, because we have decided that we will open this plant for the public. And this is done in 2 different ways. The solution on the left is as I said, some kind of a park on top, and the one on the right is more like it's a ridge where you can walk around and you can see the plant. We have very strict effluent demands from the new plant, and that's because we are not allowed, even if the city is growing from 350,000 to 600,000, then we can't totally per year pollute more by our effluent than we're doing today. So we will actually have to treat the water much better in the future. We also have to treat for reducing micropollutants like pharmaceuticals and PFAS, and even for the return pumping to the small creeks, we have to treat for some kind of different metals. So to meet the effluent demands for nutrients, we have a 3-stage plant consisting of primary, secondary, and tertiary treatment. And to handle the micropollutants, we have ozonation and granular activated coal for the quaternary step. And then for this small amount of water returned to the creeks, we also have treatment by ion exchange. So it's quite advanced treatment. And this is quite challenging because it has a very high impact on the plant footprint, on the energy consumption, on the CO2 footprint, and of course on the capex and opex. So it's really demanding to have all these strict effluent demands. This is the plant layout. If we take it from top left, then we have the mechanical pretreatment. Where we are removing sand, grit, and grease, and we also have external sand and sludge delivered to our plant. And it's actually to take stuff out of the wastewater, so we are not having problems in the downstream processes. Then we have primary treatment. Here we are removing a lot of suspended solids, and we are harvesting carbon for our biogas production, and also to reduce the load on the secondary treatment. And the secondary treatment is actually the nutrient removal. And it's the square part in the middle. Sorry. Then of course we have the tertiary, quaternary, and quinary treatment, and at the pink square up there. And we have all of the sludge treatment, utilizing the sludge for biogas production. We have digesters, we have CHP units, and we have dewatering of sludge. And then to the far right, we have what we call a resource building, because we have a vision of creating we say the world's most resource effective wastewater treatment plant. And that be big words, but what we have in mind is actually what I have listed on the slide. Biogas for power and heat, internal use, and for the grid. That's actually what we do today also on our existing plants. We could also use the biogas to put on the grid, the gas grid. Then we could produce heat for the grid from the treated wastewater from using heat pumps. And we could produce polymers extracted from the sludge called EPS. We can take out phosphorus recovery from the sludge. We have to deal with CO2, so we also plan to make CO2 capture and maybe even reuse of CO2. Then we treat wastewater and use it for internal purposes, for technical water, of course, to reduce the amount of potable water. And as I mentioned, we are also feeding these creeks with treated water. We deliver treated wastewater for vacuum trucks and for the flushing pipelines in the city and so forth. Unfortunately, the power to X is actually not very actual here in Aarhus. So that's not a direction we are looking into here for the moment. Of course, all these resource recovery technologies would have to have a positive business case to be implemented. So that's actually what we're working on, to not only develop the technology, but also develop the market, because we need to have a positive business case for implementing them. And this is a PFD of the same, so I won't go into details, but you can somehow see on this slide that we have started dividing the treatment plant into what we could call main systems. Brings me to the background for our decision to actually work with systems engineering and to start using the standard 81346. And as you can see, it's a large plant. It's a 5-stage plant. All our other plants are actually only 3-stage plants. It's with a high degree of complexity. We are doing the project with several partners, also international partners. So a lot of people will actually participate in the design and construction. And actually to design, construct, operate, and maintain the plant, it will demand a very systematic approach. And I promised Henrik to say a common language is needed. And it certainly is. And the standard, I'll just call it the standard from now on. Is that okay? The standard offers an international standard with logical system breakdown. And it's the perfect foundation for working with systems engineering as we see it, with its 4 different aspects of defining a component: the functional, the location, the product, and type. And we must just say that our existing tax system on our existing infrastructure is not sufficient to contain all that information that is needed. So we had to find something else to do. And it was actually an executive decision here in the company to go in that direction because, okay, we can do this large plant, but we have 4 plants, and in the future we have 2 plants, and then we have 200 pumping stations, and we have 10 waterworks, and we have a lot of pipelines. And so if we decide to do this on ReWater, then it have some implication on the rest of the business. So that's why it was an executive decision to do it. And of course, all these tags, which I'm not supposed to call it, is called reference design. Yeah, okay. They're used in PLCs and in SCADA and in MMS, MMC, and CMS systems. So it has huge implications to change these things. And then we have decided to use the existing AO wastewater treatment plant, which is going to survive actually in the future. So we are going to use that as a pilot plant for implementing this work with the standard, so that we get ready to use it on ReWater. Then I'll tell you a little about our use of the reference model in the project. First, we started creating a handbook, how to use RDS, how to use the standard in Aarhus Vand. And it's defining. We have all these tables in the standard with the different codes on the different levels: main systems, technical systems, component systems, and we have all these standard definitions of all these kinds of systems and whatever. And then we say, okay, but in Aarhus Vand, how do we understand it here in the house? So everybody uses the same codes for a pump or for a heat exchanger or whatever. So that was a work we did before we started. And we have made descriptions of how to use the localization aspect and the functional aspect. That's actually what we have done until now. And of course, I don't know how many you're probably using this standard. Everybody is using this standard, or what? Yeah, okay. So this is actually not something to show to you, but here's why you can find more about it. And you can also download the app for iOS and Android. This is actually, again, the wastewater treatment plant. Decided that everything in the water line is called F. Everything in the sludge line is called G. And energy production is E, and so forth. And here is actually the whole plant divided into main systems. And this is a definition we have put into our handbook. And then I'll focus on the sludge line G. And G, so the sludge line is divided into 4 main systems. And I should probably say that we are not wasting a level on just saying G for the sludge system. We are going into the primary sludge system, the secondary sludge, and so forth. So yeah, to save levels. This is a PFD of the systems G1, G2, G3, and G4. And for instance, here we have 4 digesters. And we have G3, which is digester of sludge. And we have HA1, which is digester number 1. And then we have a circulation pump and a heat exchanger for that system. And of course, when we're going to build this new digester in the future, we just have to change HA1 to HA5 and then replicate the whole thing. So that's why we think it's excellent to work with this. It's very systematic. This is how it looks we're using the sec hub from, I don't know if you're familiar with that, from the young man in the behind with not so much hair on the head. Here you see the functional aspect, all the systems, and here you have G3, and you can see here where it's located. It's actually located in the yard number 2, which is called ++P4. So you have this connection between the different aspects, and this is actually handled in this sec hub. Then we did high-level system integration analysis because we're going to procure and tender out these different system packages of the plant. And it's important to put these technologies into packages with not too many interfaces between the packages. So we try to, also as a pilot, of course, to try to work with it, to do this N2 exercise. And I think you are familiar with the N2 diagram. That we have the systems horizontal and the systems vertical, and then across, and then you can map them together, system number 1 with system number 2 and 3 and 4 and 5. And then it's actually very simple. You have inputs and outputs, and when you go left and down, you have outputs from system 1 to system 2 in this example. And it's, of course, an input to system 2. And then when you go left and up, it's output from system number 2 and input to system number 1. So it's actually simple. And we have used some classifications of the interfaces listed in the table on the left. For instance, A is a transfer of data, and D is transfer of material. And material can be gas, liquid, solids, for instance. And we also have annotated the interfaces about the knowledge. What do we know? Blank is actually we don't actually know at the moment what if there's an interface or not. Minus is actually there is no interface between the systems. A question mark is we think there is an interface, but we are not yet familiar with the kind of it or what it actually consists of. And then if we know that there are an interface, then we classify it like in the table in the bottom here. And this is what it looks like in the sec hub. It's another module, the first one with with the structure was core, and this is CMO. And here you can see all the interfaces between the systems. For instance, we have between system F7 and F6, we have a liquid material transfer. And this is the result of this analysis and the conclusion of it. Actually, we have 135 technical systems at level number 2 in the plant. This gives more than 18,000 potential interfaces. And we thought, Jesus, we're not going to do this right now. So we went to level number 1, the main systems, and we said, okay, we can try to find the interfaces between the main systems. And if there is an interface between 2 main systems, then we can go deeper and see which of the technical systems is actually interfacing. And this gives us 27 main systems. Now we have 700 potential interfaces. Okay, that's many, but it's doable. So we did that, and we actually found out that in reality, we had 166 real interfaces. Okay, now we can handle it. And we evaluated the complexity of the individual interface, 1, 2, or 3. Is it simple? Is it a little complex, or is it very complex? And we have also noted that in this result. And also the interfaces with the question mark is actually very interesting, because we know there's an interface, but we don't know what it is. But we certainly have to dig down and find out what it is. So this was actually used for trying to make the best packaging of these technologies in the tender process that we're going to do. And here you can actually see the systems with which we actually think is the most critical systems, the systems with the most interfaces. And it might not be so strange, because it's actually some of the more infrastructural systems, like the technical water, like the power supply, like the process automation system. Of course, it has a lot of interfaces with all the other systems. Okay, now I think my time is about to, are we on time, Henry? I just use a little words about what we think is going to happen in the next half year. Right now, the project is actually in between an outline proposal and a project proposal. So we are in a very preliminary phase right now still. So right now we are actually wondering what we're going to do in the next phases of the project. We will carry out a more complete system integration, also taking into account the more critical main building systems, because this is actually the process systems that we have been dealing with. And then we'll go to the next level, more strategic. From the main level analysis, we will point out where we are going to go into the next level detail, so to speak. And then we'll use the system integration analysis to formulate specific functional requirements for the technology packages. And then, of course, we will tender out these supply packages. So that's what we're going to do here in the next 6 months or so. On the longer term, we have decided to implement the systems engineering concept from your company into the project. And actually, in the tender documents, we are going to make it a demand that the companies, the suppliers, are actually using this way of working as a common language, as a common way of working into the project, because we are going to have a lot of technology packages, and it's very important that we're talking the same language. Then, of course, we are going to appoint a system responsible for each main or subsystem. And we are going to start obtaining a mutual understanding of the system requirements, because we as a client can say we want this and we want that, but do the suppliers actually understand what it is, and do we actually know how to give them the right demands? So there's a process there, actually working with the requirements. Then we're going to have speed dating for systems. This circular approaches where we are actually putting these system responsibles together and actually discussing how to make these systems function together. And it might be strange to say, but I think it's important to know what we know, but it's even more important to know what we don't know. And that might have been the last thing I should say. I have a little more, but and then of course we're going to implement the standard on all other assets in Aarhus Vand. And my last slide. We have just started, and we actually expect to gain a lot of value and knowledge from systems engineering in the coming years. We are amateurs, but we are reaching out to gain experience from whoever is working with this. So that's all from me. Thank you.
So thank you very much, Henrik. There's a lot of things we assume people understand, the N2 diagram, system thinking, system breakdown, and stuff like that. So we assume you know that. If not, you have to figure that out yourself if that's not the case. Anyway, there's time for questions, and I'll also try to see if I can manage to handle the remote partitioners as well. But I would like to go to your N2 diagram and the system integration analysis that we have done together with you, because I know when we did that was we discovered a minor mistake. Maybe you can talk about that, what we actually discovered by doing that analysis.
We actually found out that we had missed totally out a whole pumping station in the system, and we actually found that out in doing this exercise with the N2. There was just something totally missing.
The value of how much?
10 million.
Forgot it, but now we discovered it again. So that's, I mean, just that simple exercise. We forgot that, but we found it on a piece of paper. So no harm done. And nobody thought of it. So that's very nice. So now it's time for questions. And as you know, we have partitioners remotely. I'll see if I can handle that. But here, if there are any questions in here, you need to speak in the microphone. So if anyone has a question, please raise your hand. Or was it clear? Yeah, Bitten has, so you need to speak in this one, Bitten. So it comes to you. I can repeat your question. Yes, please. So the question is, in the 81346 standard, which part of the standard are you using here?
We are using we're using it to do the reference designation, actually to put on the codes in the functional aspect and in the location aspect. We are not using the two other aspects at the moment, but I think we are going to. Okay, we're using the number 12. Yeah.
So it's because for those
CW.
of you who don't understand that, it has several different kind of industry specific. We have part 10 for power systems. We have part 12 for construction works, which fits quite nicely with the simple process after all you do. We have part 14 for manufacturing system, which is relatively new, and there are 2 more pending as well. And then there's the generic one. Okay.
But we're also doing something using something from the number 2, the component vehicles and that.
Any questions from our remote practitioners, please write it in the chat and I will record it here and repeat it. So please feel free to ask any questions.
Oh, I had one here.
Otherwise, you can think of it and you can always get back to it. Regarding the sharing of systems engineering, you also told that in the presentation, but we have been talking quite a lot about the complexity of your project, and I'm not sure if it's clear to you how big it is, but the value today and the estimated price.
I don't know if I dare to say it, but it's about 6.5 billion.
6.5 billion Danish kroner to establish that kind of plant, and if you don't do it, you have a major problem.
Yeah, because then the city can't grow.
And I also think we have been discussing a lot about the requirements in the increasing requirements of cleaning the wastewater has gone up dramatically.
Yeah.
So nice to say you need to clean for all that PFSA and all that stuff, but in reality, it costs a lot of money and complexity. Maybe you can say a few words about that.
Just the thing about doing the cleaning for the micropollutants and the PFAS and the metals, the 4th and 5th step, it's 1 billion.
It's about 1 billion Danish kroner. It sounds so nice when the politician says just clean it, but in reality, when the bill comes, and who's going to pay for it, by the way?
You and me. No, I'm not living here. You are not living here, but people living here.
So there's no government coming and funding it. It has to be for the users. That's also why you say you need to create the business case.
Yeah, for the resource recovery. The other stuff is just do it. You have to go and do it.
Yeah. So that's something we maybe don't think about in the green energy. Somebody has to pay for it, but I think that's also why there's a pressure on you to, if you start the project, there's a hard pressure on you to deliver on time, to keep the budget, and to make sure it actually works when you plug it in, literally.
3 important things.
Yeah. And for that purpose, you say systems engineering must be your way around.
Yeah.
Now that question comes, that's nice. I'll try to, if you ask the question, I'll repeat it here, and then you can reply on it. Yes. Great. So, but was that the question? Okay, thank you very much. Yes, please.
I'm sure it will be, yeah.
So
we have not done the tender material yet, but I think it's something we have to note.
Just to repeat the question for our recording, the question was that if you're going to tender out and going to work according to systems engineering disciplines, that's also a requirement you'll put on the tender documents for your tenders to bid in on the project as well. And the answer is yes, we'll need to do that. Yeah. Yes, please. In the back seat, please.
No,
just a moment to repeat. First, it's a little bit complicated. The question is regarding the handbook about the 843 fix. How is it developed? Is it internally, or did you actually onboard your external all your stakeholders in general? Yeah.
That was internal stakeholders, so people in the house.
So that was the first question, and the second question. So the question is, when you have made this breakdown with, we call it main systems and technical systems according to the standard, how do you handle the requirements related to that one?
Actually, we have not handled that yet, because these suppliers, they're not here right now. So there are no one to speak to.
Should I support you here, Henrik?
Yeah.
So the question is how we actually manage. There are requirements, of course there are requirements, but I think the trick here is that what we like to do as well together is that instead of trying to just list down the requirements and then try to figure out the systems related to it, we turn it upside down. So we first do the reference model that you saw before, created on 81346. And that means that any requirements that are floating around you in documents or in emails or whatever is on documents, they have to be related to a certain system. Otherwise, the system doesn't exist or is not represented, or vice versa. There's a missing requirement. So speaking as a systems engineer, and you usually do the requirement breakdown first, and then you do the systems. But in reality, we know most of the systems already from a functional point of view. So what we are working with and what we typically do and recommend is that you make the reference model based on systems breakdown according to this international standard. And when you've done that, then you got a perfect place to hook up your requirements later on. So that's how it's handled in reality. There was a question from, was it you, Jens Christian? Yeah. The question is, we talk about system owners, which is also a principle we like to use. And if you had that before we started the system breakdown, or how it works?
Actually, this was a pilot exercise, and we also had appointed. I was a system owner. Some of my colleagues had ownership for systems, and then we actually did that into that N2 exercise. So, but of course, we are going to appoint system owners from the actually organization that's going to design and construct the plant when we come to that. This was more like an exercise.
Yeah. Then I'll take some questions from the online audience. The first question is, have you made a full RFLP breakdown with a full traceability, or just kept it to the physical structure? The RFLP model, we haven't discussed that, so I don't think you know what that is, but that is a certain extended version of the reference model. So if you don't mind, I will answer on your behalf. No, we have made only a functional breakdown to beginning, because that's the most starting point, so to speak, and that's enough for now. We've also tried, we have discussed a lot, we have tried a lot to make sure that we can onboard people to the model, so it's not complicated, something that people really like and can see themselves in. That's also one of the reasons to keep it as simple as possible. So the answer is no, we haven't made that. We have done it in some other projects, but not here. And the second question from Daniel, how common is it to avoid levels by putting information in numbers? The guideline is to avoid that. Daniel, I'm not so sure I completely understand your question, but the thing is that to be practical, I would say we just follow strictly the rules from 81346, how that works. That also means we avoid putting a meaning into numbers, and just simply by following the standard and the way it is developed today, it actually is not a problem at all. It's no problem.
And I might say that that's one of the things that a few of my colleagues are troubling with, because when you have all these main systems, then you have a natural flow through the plant, and almost everything is gravitating. The water is gravitating from one stage to another stage, and if you're putting one in between, then you almost can't live without changing the numbers. But you shouldn't change the numbers. You should just put a new number. So that's
that's the answer to that. Yeah. Don't put meaning into numbers. That's a mantra of ours. All right. So there's the last question. Where can we find the interaction tables with the corresponding codes used in the diagram N2? The answer is on our software. It's a part of that one, to be practical. So no more questions in here. One more question in the back seat. Yes, please. The last one, please. So the question is regarding the interfaces and the huge amount of interfaces, if we are going to revisit, or you are going to revisit them later on. I actually think you will.
We are.
Yeah, but the answer is yes.
Yes.
For sure. All right, we are good at keeping time. So now it's 4 o'clock, and now we'll have a break for networking and time for asking additional questions as well. So, and also for your online practitioners, we will have a break for half an hour now until 4:30. And when we get back, we will listen to the presentation from Makeen and their plastic to oil conversion plant, which is super interesting. I really look forward to that myself. So for now, we will have half an hour with breaks. There are more cookies on the table. There's coffee in the machine. And if you need water, there's water on the watering taps in the end. So we'll meet in half an hour when I ring the bell. Ding, ding. So have a nice break.